So physicist Brian Cox just came on The Big Think and had a great video and explanation about quantum mechanics and quantum computers. And I love that more and more we're seeing that these are being discussed in the mainstream. The video already has, let's take a look here, 280,000 views and lots of engagement and likes. I want to do a react on some of my favorite parts of the video. So without further ado, let's jump in. If you like content like this, please consider leaving a like.
In the subatomic world and the world that we observe, this world of common sense, let's say, that we perceive. And it's pretty well understood, I would say it's well understood, how the world that we see emerges from this rather strange but well-defined behavior that we see in the subatomic world. And it's not only the subatomic world, by the way. We have an increasing number of quantum technologies that are really based on this behavior. Quantum computers being a good example. And so you see that this is not just something that you can say, well, we don't need to think about it really because it's in the world of atoms, because we're using that behavior now in technologies. And so it really does become an important theory to try to understand.
Why is it important that we seek to solve the mysteries of quantum physics?
You could argue that even today, the interpretation of what the theory is telling us about the nature of reality itself is not universally agreed upon. One of the big changes, actually, that's happened in teaching quantum mechanics in universities over the last few decades is that it was always, when I learned it, so back even in the 1990s, it was common to teach.
All right, so first we're going to look at the quantum slit experiment. If you haven't heard about this, Brian is going to explain in detail, but it is fascinating and it's going to be a nice foundation for us to move through the video so we can talk about some of these concepts. Let's take a look.
If you look at pretty much any book on quantum mechanics, there is one experiment which you can describe. It's a very simple experiment which encapsulates all the I was going to say weirdness, but it's all, let's say, all the properties of the quantum world. It's called the double-slit experiment. And by the way, I'll strongly recommend, I think it's almost universally accepted, the best description of the double-slit experiment is freely available. It's in the Feynman Lectures, Volume 3, first chapter. And I've read quantum mechanics textbooks that say, go away and read the first two chapters of the Feynman Lectures on Physics, Volume 3, because it's all in there. Can't be done any better. So I could recommend that if you find this interesting. The double-slit experiment is essentially, let's say you have something that will emit, let's say electrons, so particles, electrons, electron gun that emits particles. And then you have a barrier that has two slits cut in it and a screen. So that's the setup of the experiment. So we have something that emits electrons, two slits cut in a screen, and a detector, another screen that the electrons will hit. So you fire the electrons out. So what will that look like? Well, if you think of the electrons as just little particles, little bullets, let's say, that are emitted from this gun, then you would imagine that the electrons can go through one slit or the other one, depending on how they come out. And you can imagine that they might get deflected around a little bit when they go through the slits. But basically, on the screen, you would expect most of the electrons to appear opposite one or the other of the slits, with maybe a bit of a spread because they rattle around a bit when they go through. So you get lots here, and pretty much none in the middle. But that's not what you see. What you see is a very clear pattern on the screen. You see sort of stripes, a stripe on the screen where you get lots of electrons, and then a stripe where you get very few or none. and then another stripe where you get lots, and then a stripe where you get very few or none, and then another stripe, and then very few or none. So you get this stripy pattern. That pattern is exactly the same pattern that you would get if you sent waves through the slits. Let's say water waves, any kind of waves. Then it's easy to understand, because what's happening then, and physicists knew this back in the 1700s, right, is that you can consider each slit as a source of new waves. And the waves come out, and waves have the property that they can interfere with each other. So you can get the peak of one wave arriving at the screen from one slit, and a trough of a wave arriving at the screen from another slit. And if everything's lined up correctly, the peak and the trough cancel out and you get nothing. So you get this property where something from each extended wavy thing lines up in such a way that it cancels out. And then it could line up in such a way that it reinforces, and you get a big disturbance there. And then it cancels out again, and then it reinforces again. So you can imagine this stripy pattern on the screen. That's what you get with waves. The fact that you get it from particles is interesting. But here's another interesting thing. You still get that pattern if you send one particle at a time through the slits. So it is, and let me use my language carefully. I was going to say it is as if the electron can somehow explore both paths, just like a wave can, and then interfere with itself to control where it lands on the screen. As if is something that people might object to. Many physicists would say, no, it does. So the statement is that the electron explores both routes at the same time, at once.
And Michio talks about this a lot in his book, Quantum Supremacy, which I think if you're interested in this topic, if you're seriously interested in quantum computers, you should pick up that book and just read it. Read it with me. I'm still 10 chapters in, but I've learned so much from it. I will do some content on the book when I'm done with it. It is densely packed. But essentially, what I think he talks about here, I can't remember in this video, but essentially once the particle or that photon is observed, then it has to choose a path. So there's something about observation that changes the behavior of all this observation or measurement. Let's take a look.
Let's say, on its route from the electron gun through the slits to the screen. So that's a very strange picture of reality. We surely think of particles as following definite paths. And it might be that you don't know quite which path it's going to take, but surely you would say, in reality, it will go one route or the other route. But that experiment, which I emphasize has been done now many times, tells us that nature is not like that. It tells us that the electron must, in some sense, explore all routes on the way from the gun to the screen. And so the question then becomes, well, what do I mean by in some sense? What you'll see in the Feynman lectures is he gives you two pictures of how to think about physics. One is he gives you the way that you would calculate what you're going to see on the screen. And that's really simple, as Feynman points out. So what you can do is you can calculate what's called a complex number for every route that the particle, the electron, can take from gun through the slits to the screen. So every route, every path it can possibly take. A complex number, for those that don't know about complex numbers, can be pictured as a little clock face. So a complex number has a clock hand, there's a length of the clock hand, and there's the time on the clock face. And you can calculate how those clock faces kind of evolve and change and spin around from the moment the electron's emitted to the moment it hits the screen. And the prescription is very simple. You can calculate what those clock faces look like, what those complex numbers are. And at every point on the screen, you have to take them all, every possible path to that point, and just add them up. And the length of the clock hand gives you the probability to find the electron there. It's actually the squared length of the clock hand that we perceive. There aren't different rules. And it's pretty well understood.
So now Brian is going to talk about the atomic versus the subatomic world and the different rules and properties that apply to that world. So let's take a look.
I would say it's well understood how the world that we see emerges from this rather strange but well-defined behavior that we see in the subatomic world. And it's not only the subatomic world, by the way. This is now, maybe you could have argued 50 years ago that this is just all philosophy, it doesn't really matter, whatever. But now we have an increasing number of quantum technologies that are really based on this behavior. The quantum computers being a good example.
That's us.
And so you see that this is not just something that you can say, well, we don't need to think about it really because it's in the world of atoms and it's all a bit whatever, and we can just do some calculations, because we're using that behavior now in technologies. And so it really does become an important theory to try to understand. Now, you go back a few decades, then I think you could say that the interpretations of quantum mechanics are very interesting and very important because we're talking about the nature of reality. But you might say, well, it doesn't really matter so much practically, right? Now, I have a lot of colleagues in physics who would, I think rightly, hate that description because what we're trying to do is understand reality, what physics is. But now, particularly, I think, with the possibility of building quantum computers, this attempt to understand how large systems of quantum mechanical objects behave is becoming extremely important, because a quantum computer is a device which is built out of qubits.
This may be the single best explanation of qubits without a diagram or without a visual representation that I have ever seen. So enjoy this part. Brian absolutely killed it.
So remember, a qubit, an example would be an electron, which has this property that when you make an observation of the spin, let's say, of this electron, it behaves like a coin. It can be up or down, heads or tails, however you want to describe it. But that thing can also exist in a superposition, a combination of these things. And it's a perfectly valid configuration. And you use that. That's the kind of property that you use in building a quantum computer. You can also then ask the question, well, what happens if I get another one, two electrons together? These can be in what's called an entangled state. So then you have a much richer structure of this physical system. So an example of an entangled state, a very famous thing called a Bell state, would be where you set these things up. So the system of these two qubits, let's say they're up and down, these spins, right? So I can have the state up, down, plus, down, up, like that. A complete description of this state. Up, down, plus, down, up. What does that mean? So let's say I take one of these electrons and I separate them. It's a very famous paper written by Einstein, Podolsky, and Rosen that first considered this in the 1930s. And they get very upset by the behavior. So we've got a system, a state, and it's up, down, plus, down, up, let's say. And I separate these electrons. I take one to, let's say, to Pluto and leave one on planet Earth, right? And then, so what's the description of this thing in that state? Well, it's got, in the way I described it, there's a 50-50 chance that when I make a measurement of this electron, the up or downness of it, then there's a 50-50 chance it'll be either up or down. And the same for the other one. That's what that state means. But if it's up, down, plus, down, up, then it means that if I make a measurement of that one, if I say, well, okay, I know what that is, it's up. The other one has to be down. Up, down, or down, up. It can't be up as well. Same for the other one. If I go to Pluto and have a look at this one and it's down, then this one definitely is up, right? So this is called quantum entanglement. And the reason it bothered Einstein and others is it would appear that something is instantaneously changing. And it's not just your knowledge of the system that's instantaneously changing. It would seem that the system itself is instantly configuring itself when you make some measurement. So you might say, well, this is nonsense. There must be something else. And it turns out that as far as we can tell, and a Nobel Prize was awarded for some of this research a few years ago. Then no, there's nothing hidden there. This is the way that the system is. But you think about that system of 2 qubits. Right? Think about it. So you've got these two things which can be up or down. There are 4 possible combinations of that system. You can have up, down, up, or down. 4 for the 2 qubit system. For a 3 qubit system, you think about it, ups and downs, you'll find out there are 8 possible combinations and all mixtures of them. For 4 qubits, then it's 2 to the power 4. There's 16 possible combinations. We're talking about building quantum computers now in which we have 100, 200, 300 qubits, all in principle entangled together. The number of possible descriptions of that system, then, you have numbers that describe it. If there are 100, it's 2 to the power 100 different configurations and any mixture of those things that are states of the system. So pretty soon, 2 to the power 100 for 100 qubits. What's the number of atoms in the universe? If you had 2 to the 500, you'd far exceed 500 qubits. The number of numbers you need to describe that system exceeds the number of atoms in the observable universe. But it's a thing that we can build. We can build just about. We're not far off being able to conceive, at least, of a network of 500 qubits. They're physical things. They're kind of like that big, some of them, right? So you go 5.
Crazy, right? So every time you add a qubit, it exponentially increases the power of the quantum computer, which I think is the main takeaway from that, or one of the takeaways. But the fact that we as humans are literally doing compute through atoms is an insanely significant scientific milestone, and just shows how brilliant humans are when we focus on the science and when we try to move forward our understanding of science and the greater, the universe, to be quite frank.
So the power that's hidden in the description of a system like that is immense. And the thing that a quantum computer does is it uses that power, some of that power, some of that vast computational or configurational power of the thing. It's very, very difficult to do. And we've not been able to do it particularly well at the moment. You'll read many papers online where obviously companies like Google, Microsoft, IBM are investing a lot of money in these devices because potentially they can carry out computations that no conceivable classical computer could make within the lifetime of the universe because of this tremendous freedom in the description of the structure of the system. So quantum mechanics and quantum entanglement, these properties of matter, of nature, are becoming very real because we're beginning to be able to access this tremendously complicated configuration space to do useful things, to make calculations that are useful to us.
Want to support the channel?
Okay, guys. So that was a super fun one. And we see the media, right? And these big interviews. Don't be surprised if you're seeing more and more physicists start coming out and doing interviews like this as this quantum theme gains momentum and interest even from the public. Right now, it's very important that we educate ourselves on what it is and what it's going to mean for the world. So if you're interested in that type of information, Please consider leaving a like or subscribe if I've earned it. Have a great weekend.